Heyo. All right, number three. We have Physics Phil and Science Steve. They're trying to move a couch together, but they're not doing a very good job. The couch has a weight of 100 newtons. It's currently at rest. Phil pulls on the couch to the east with 40 newtons of force. Phil pulls the couch to the west with 15 newtons of force. They try and pull this weight for about 3 seconds. Okay, so they're kind of having a tug of war with this couch. First thing we wanted to do was draw a free body diagram of the couch. We want to know what is the net force that the couch experiences, what is the couch's change in momentum, what is the couch's mass, because it doesn't actually tell us that right out, and then we want to know how fast is the couch moving after this attempt to move it. Okay, so there is a whole lot of things going on with this couch. A free body diagram is probably the best way to get started. So I've gone ahead and filled in everything that I know about this interaction. I know that we can model the couch's motion before, we can model its motion afterwards, and thanks to forces, we can model what's happening during that interaction. Remember, an interaction is any type of contact between two or more bodies. Okay, in this case, Phil and Steve are interacting with the couch. So each of these force vectors represents those interactions. I've drawn Phil's applied force of 40 newtons to the east, and then I've applied Steve's force 15 newtons to the west. Notice that I've made these vectors slightly different sizes to reflect their magnitudes, okay, and also their directions. The question also said that the couch has a weight of 100 newtons. Remember that weight is just a object's interaction with gravity. Oh, I had an equation. The object's interaction with gravity. Okay, so you have a certain mass, and your weight is different than your mass because your mass is just a measure of how much stuff you have. Your weight is a measurement of your stuff interacting with a gravitational field. Okay, and to just kind of save this for later, we could say that the force of gravity, right, that's equal to your object's mass times its interaction with gravity. Okay, so because weight is a force, okay, the force of gravity, we're assuming our couch is on the ground, so it's also going to have a normal force or a support force in the equal and opposite direction. Okay, so I've drawn my normal force going upwards. So you'll notice that these guys are the same size, so they cancel each other out. So this can bring us to part B, right? What is the net force that the couch experiences? So we're taking all of those interactions, we're adding them together, and it is like a big game of tug of war. Okay, whichever side has the most newtons applied, right, is kind of the winner. That's where the net force is going to go. So there is no net force up or down because they cancel each other out, but we can say that there's a net force from west to east, right? So if you have 15 newtons going west and 40 newtons going east, the overall net force is the difference between these two, right? How much bigger is the east force than the west force? Okay, so if we subtract 40 and 15, we should get a net force of 25. Okay, so everything going to the west, or everything going to the east, is 25 newtons greater than what's going to the west. So that is going to be our overall net force, 25 newtons west. Okay, that's newtons, not north. That's north. Okay, so now we have to figure out what is the couch's change in momentum. Okay, we know that if we're experiencing a net force going to the eastward direction, this couch is going to experience a change in motion. Okay, a change in momentum. So we can calculate the change in momentum by using the net force and the amount of time that it's been applied. Okay, so our change in momentum here, we've got a net force of 25. And that's 25 newtons, and then we're going to multiply it by the change in time, which was 3 seconds. Okay, so 25 times 3 gives us 75. Sorry, I'm running out of room here. Okay, 75, and because this is momentum, it's going to be kilogram meters per second. Okay, so that takes care of this first bit, that takes care of the second, the third bit. Now we want to know what is the couch's mass. Okay, so the question doesn't give us anything specific about the mass, but it does give us, again, its weight, right? It has a weight of 100 newtons. And I said earlier that weight, just the force of gravity, that's your mass times gravity. Okay, so if we know the weight, we know the interaction with gravity, g, which is always 10, we can easily solve for mass. Okay, so I'll just leave this here. So if our weight was 100 newtons, our mass is going to be at times the field of gravity, which is 10. Okay, so we just have to ask ourselves, what times 10 gives us 100? So we should get 10 kilograms for the mass, right? So 10 kilograms, that is equal to our mass. Okay, so we're good with that one. So now that I know this, I'm just going to fill it in on my diagram. 10 kilograms, 10 kilograms. Okay. We know that the couch was initially at rest. Okay, it said that in the question, currently at rest, so it starts off here. And yeah, that could tell us that our initial momentum is 0. Okay. So this final question wants to know, well, how fast is the couch moving after the attempt to move it? Okay, they've been having this tug of war for 3 seconds. How fast is it moving after those 3 seconds? So we have all of these pieces. The only thing that we're missing now is our velocity, but we can figure that out by checking out our change in momentum. Okay, we calculated earlier that the change in momentum was 75 kilogram meters per second. Okay, so if we start at 0 and we experience a change of positive 75, that means our final momentum is also going to be a positive 75 kilogram meters per second. Okay, and using our momentum equation, okay, momentum is equal to mass times velocity, we now have all the details to figure out the final velocity. Okay, I'm just going to set that over here. So my momentum was 75, and that's equal to the mass, which was 10, times my velocity. Okay, so what times 10 gives us 75? Well, if we divide both sides by 10, we should get 7.5, right? So that is our final velocity. 7.5 meters per second. Bam. And that's all we got.